Hey everyone, welcome back and let's write some more NeetCode today. So today I want to run through all of the common big O runtime complexities that you'll need for coding interviews. And by the way, all of the code from this video will be available for free on neetcode.io. If you're not familiar with it, it's basically a site that I created. It's got a ton of free content to help you prepare for coding interviews, including code in Python, JavaScript, Java, and C++. And I've also started making courses. So far, I completed the Data Structures and Algorithms for Beginners course and the Advanced Algorithms course, and I just started uploading the System Design for Beginners course. You can use code NEET for 10% off lifetime access. That means you'll have lifetime access to all current and future courses. So first of all, what even is big O time complexity? Well, it's basically a way of analyzing the runtime, the amount of time it takes for our algorithm to execute as the input size of our algorithm grows. Typically, we can expect as the input size of our algorithm grows, the execution time of the algorithm is also going to grow, but it could grow linearly, which, this is a function you might be familiar with. We're used to y equals x. In terms of big O, this is represented as big O of n, where n is just a single variable. That's our x-axis. Now, this is where we take a different turn from algebra. You could have another function like this, which is, for example, n divided by 2, but we actually don't care about the differences when those differences are constant values. We only care about the variable here, which is n. We don't care about the divided by 2. And that's true for all big O runtimes. We also don't care if, we have n plus some constant like 5. Like that might look something like this on our chart. It just starts at a different spot and has the same exact slope, but we don't care about these constants either. So the first runtime we're going to look at is big O of 1. I know we said that we don't care about constants, but in this case, 1 is a special constant that we do care about. And as you can tell from the chart, no matter how much our input size grows, the time complexity of big O of 1 time algorithms is always the same. You can see it's a flat line because the time it takes for these algorithms does not change based on the input size. These are the most efficient algorithms. So for example, if you have an array of values like this, it's a constant time operation to add to the end. It's also a constant time operation to remove from the end, or just to search an arbitrary index, just to look up a value at any index, whether it's at 0 or 1 or 2. And the same is true typically for a hash map. So to insert any value into a hash map is constant time. To look up a key from a hash map is also constant time. And to remove a key from a hash map is also a constant time operation. And the same operations could be applied to hash sets as well. We also have big O of n, which as we discussed is the linear growth scenario. So as our input size grows, our time is going to grow proportionately. So if we're given some array of values and we want to take the sum of all of those values, this sum function is going to be a linear time algorithm because we're going to have to go through every single number in the array. So with just 3 values, it won't be too bad. But as our input size grows, so if our array had 1,000,000 values in it, so then the runtime of calculating the sum would also grow. And of course, we know that's going to happen because under the hood, we're going to have to loop through all of the elements. So looping through a list of elements is also a linear time algorithm. Inserting in the middle of an array and removing from the middle of an array is also big O of n. And that's because when we talk about big O of n, we mean the worst case runtime. Because in some cases, like inserting in the middle, well, for example, inserting in the middle of this array could be over here, in which case we would have to, put a value. Let's say we're inserting the value 100. We'd put 100 over here and then move the 3 into the next position. And then this would be our new array. So in this case, we only had to move a single value. But what about if we wanted to insert the 100 over here? Then we would have to insert the 100 here. We'd have to move the 1 to the right. We'd have to move the 2 to the right. And we'd have to move the 3 to the right so that this would be our new array. And in this example, we had to move every single value in the array. We know that's an n time operation. So since we don't know where we might insert in the middle, we take the worst possible case, which would be big O of n in this case. Also, removing from the middle is going to be similar. If we remove from the end, it's a constant time operation. But if we move from an arbitrary position, for example, the first position, then we would have to shift every other value to the left, and we'd end up with an array that looks like this. Now, searching an array is also a linear time algorithm. In the worst case, we would have to look at every single element in the array before we realize that the element, in this case, if we're looking for 100, doesn't exist. It didn't exist anywhere, and we had to look through the entire array to figure that out. Or we might find the element. We might even find it in the first position, but we take the worst case, which is going to be big O of n. Another one that I get a lot of questions about, if you have a set of values, in this case, a list of values 1, 2, 3, and you want to heapify them, you want to build a heap out of those elements, the heapify algorithm actually runs in big O of n time. If you don't have to individually push an element to a heap, it runs more efficiently. If you can just build it from scratch, this is an n time operation. A couple more common algorithms, the sliding window algorithm also runs in linear time. And I'm actually going to quickly go on NeetCode.io over to the sliding window section. And the second problem in the list, when you take a look at the code, you see that it does have nested loops, but that doesn't necessarily mean the time complexity is n squared. A lot of people assume that just because you have nested loops, the time complexity is n squared, but that's not always the case. The same is true for the monotonic stack algorithm. So once again, going on NeetCode.io to the stack section, the daily temperatures problem is a monotonic stack problem, and it also has nested loops, but this algorithm actually runs in big O of n time. If you want more details on these problems, I recommend going to NeetCode.io. You can check out the video explanation, and I go more in depth to analyze the time complexity in each of these videos. Next, we have big O of n squared, which we kind of just talked about. When you have nested loops, the simplest case is if you actually had a two-dimensional array and you wanted to iterate over that array, you would need nested loops to do that. So for example, if we had a grid like this, 3 by 3, so you know it's squared, so this could be any arbitrary dimension, though n by n, you want to first go through every row in this grid, and then for every row, you want to go through every single position in the grid. So the outer loop is going to go through every single row, and the inner loop is going to go through every position in each individual row. And what's the size of this grid? Well, it's going to be n squared. That's how we get the big O time complexity for that. This is pretty simple. Another case that kind of trips up some beginners is if you just have a single array and you want to iterate through it n times. So if you have an array that looks like this of size n, you go through it once, that means the big O time complexity is going to be n. If you go through it twice, the time complexity is going to be 2 times n, which we know reduces to just be big O of n. But what if you iterate through this array n times? Well, then the time complexity is going to be n times n, which would be n squared. But it's actually not very common that you iterate through the entire array n times. What's more common is that you iterate through the entire array once, and then you iterate through every element in the array except the first position, and then you iterate through every element except the first 2 positions, and you keep doing this until you've just iterate through the last element. So this is a diagram of doing that. You go through 4, 3, 2, and then 1. So what would be the time complexity of doing this? Well, mathematically, this is actually a well-known series, and it can be proven that this will roughly equal n squared divided by 2. But if you're not smart enough or care about that math portion, an easier way to identify that would be, well, here we have a square, right? We have an n by n square. Now, what does this portion of the square look like to you? To me, it looks like half of a square. It basically looks like we cut this in half. So now you're probably convinced that iterating through an array like this is going to lead us to n squared divided by 2 time complexity. And like I said, we don't care about constants, so this 2 does not matter. Therefore, we say that iterating through an array like this is also n squared. A lot of people kind of brush over this, and I'm pretty sure most people never actually learn this or care about it, but that's okay because you don't really need to anyway. But now you know something that probably most people don't. We also talked about how inserting into the middle of an array is an n time operation. So insertion sort, which basically inserts into the middle of an array n times, is going to have n squared time complexity as well. Another one that's pretty similar to n squared, so I won't actually draw this one out on the grid, but n times m. This could mean a 2-dimensional matrix that's not necessarily a square. So in our example on the left over here, we could have some rectangular array that looks like this, where we have 2 rows and we have 3 columns. So in this case, n might be the number of rows, where m might be the number of columns. We actually have two variables this time, which is perfectly valid in big O notation. Now, if we can have n squared, why stop there? We can also go up to n cubed, and we could actually go higher and higher to n to the power of 4, to the power of 5, etc., but I won't do that. It's pretty uncommon to even have n cubed actually for most problems, but this is usually the highest that we get to. Usually you don't have algorithms that go up to n to the power of 4, but it's possible. And I think you would be able to identify that case if you're able to identify these as well. Of course, we could have some kind of three-dimensional data structure. More commonly, though, you'll just have a single array and you'll want to get every unique triplet from that array, for example. So in this case, we would need 3 nested loops to iterate through every single triplet from this input array. Now let's move on to some of the more complicated ones like log n. This is where we get more math involved. And I bet you most people don't know how to analyze log n time complexity. They kind of just memorize it because usually log n is applied to binary search. For example, on an array, or you could run binary search on a binary search tree. These are the two most common algorithms, but there's also pushing and popping from a heap, which is another common one. On an array, the reason binary search runs in log n time is because on every iteration of the loop, we eliminate half of the elements from like consideration. We don't need to search this half of elements, for example. So then we'd be left with 2 elements, and we could keep cutting this array basically in half until we have nothing remaining. That's when we would have completed our binary search. So the question is, given an array of size n, how many times can you cut the value n by 2? How many times can you divide it by 2 until it equals 1? Well, another way of talking about this would be, how many times can you take the value 1 and multiply it by 2 until it's equal to n, aka 2 to the power of what, x in this case, is equal to n. How do we solve this mathematically? Well, by definition, that's what log actually is. We take the log of both sides, and then we realize that x is equal to log n. So therefore, the number of times you can take an array like this and divide it by 2 is equal to log n. In this case, the base of our logarithm is going to be 2. So that's where this comes from. And the idea is the same when we were talking about binary search trees, at least if your BST is balanced, because as we search it, we're either going to go to the left or to the right looking for some target value. So if we end up going to the right, that means we eliminated the entire left half of the tree from consideration, and we do this recursively. So we start with a tree of size n, and we basically remove half of the elements from consideration until we find the target that we're looking for. That's why this is also a log n time algorithm. So log n grows pretty slowly. You can't tell from this chart, but actually for really, really large input sizes, log n is practically a flat line. Like the difference between log n and big O of n is massive. I think log base 2 of 4 billion would be something like 32. So even with an input of billions, we get a very small 2-digit number. Now we also have n multiplied by log n, and this is actually only marginally less efficient than big O of n. It's a lot more efficient than n squared, just like how log n is much more efficient than big O of n. The most common algorithms for nlogn are sorting, for example, merge sort, and we usually assume that most built-in sorting functions are nlogn. So if you need to run the built-in function in a coding interview, you can basically assume that it's an nlogn algorithm. Heap sort has the same runtime, and this kind of illustrates how we can get a runtime like this. We know that popping from a heap is a log n time operation, and if we have a heap of size n, and we have to pop from that heap while that heap is non-empty, then we end up doing n operations, which take log n each. Therefore, we get n log n as the total result. Now, in this example, before we started running the heap sort algorithm, we actually had to build the heap. So this took big O of n times. So actually, the overall runtime was n plus n log n. Should we draw that on our chart? Well, with big O notation, we only care about the larger term. If we have a term like this, which is strictly larger than this term, we don't care about the smaller term. But we could have a time complexity where we have m plus n log n. And in this case, since m is a different variable from any of the variables we have here, we don't know that this is strictly smaller than this one. So we have to include both of these in the big O time complexity, but we don't have that in this case. So we reduce the time complexity to just be n log n. Now let's get into some of the non-polynomial runtimes, which starting with the most common is 2 to the power of n. And this is the part where I could start going on a nerd tangent and talking about how this equation is actually just a reflection of the log n over, this axis, but I'm pretty sure nobody cares about that, so I won't get into it, but feel free to comment if you're interested in the math stuff. It's most common to have a runtime like this when you're talking about recursion. So this is an example of 2-branch recursion where our recursive tree will have a height of n, but we'll have 2 branches every time. So this is recursively calling some recursive function. It's not really doing anything, but here you can see we have 2 branches of recursion. Visually, it would look something like this, similar to a binary tree. But in this case, the height of this tree would be measured in terms of n. So for example, if we were given some input array of size n, and we wanted to get all possible combinations, that would be one example of 2 to the power of n runtime. So for example, computing the Fibonacci sequence recursively is a pretty common example, or combinations. Now, if we can have 2 to the power of n, can't we have 3 to the power of n? And what about 4 to the power of n? Yeah, you can have pretty much any constant, let's call it c, raised to a power of n. Now, I'm not going to draw those out, but with a bigger base value, we will have, increased runtime complexity. So an example of that would be pretty similar to our previous recursive example, but in this case, instead of having 2 branches, we have an arbitrary number of branches. So we use a loop to do that. So in this case, our constant c is going to tell us how many times we need to loop and make a recursive path. So in this case, if c was 3, we'd have a decision tree with 3 branches, and the height of the tree would continue to be n, so we would end up with a time complexity of 3 to the power of n. Now, how am I getting that time complexity from a decision tree? Well, think about it this way. If we have 3 branches on the first level, we have 3 values here. Now, for each of those, we're going to have 3 more branches. And then for each of those, we're going to have 3 more branches. We're basically going to keep doing this until we reach the entire height of the tree, which in this case is n. So we're basically going to have a number, our base value, 3, multiplied by 3, and just keep multiplying it until we have n of these. Therefore, we get 3 to the power of n. Now, a pretty rare runtime complexity is the square root of n. You rarely see this, but I still think it's worth mentioning. You will rarely ever see this in a coding interview, but I think it's still worth mentioning. The only example I think I've ever needed this for is getting all the factors of some value. So for example, if we're given a value n and we want to get all the factors of it, we will go through every value between 1 and the square root of n and check if any of those values is a factor of n. And since this could possibly produce some duplicate factors, we add those factors to a hash set, which we know is a constant time operation. So the number of times this loop is going to execute is of course going to be the square root of n. Now, I won't go super in depth on why this algorithm works. If you want to know, feel free to ask in the comments. It's really more of a math problem than a coding problem. And lastly, we have n factorial, which is a math equation, which basically means, if we had 5 factorial, that is 5 times 4 times 3 times 2 times 1. So basically it ends up being a very big number. We say that this is bigger than 2 to the power of n because 2 to the power of 5 in this case would be 2 times 2 times 2, 5 times. And you can see that just by looking at these two, since factorial has the potential for having larger terms than just some constant value 2 or 3 or 4, that this is going to grow much quicker than this one. Now, n factorial is pretty rare. It mainly comes up for permutations and sometimes in graph problems, for example, the traveling salesman problem. But I think you don't have to focus too much on n factorial. You mainly have to know that it's very inefficient. So if your solution is n factorial, most likely you don't have the optimal solution, but sometimes n factorial is the best you can do. In a real interview, I don't think it would matter too much if you can, precisely tell, is your algorithm n factorial or is it exponential to the power of n? It wouldn't matter a lot. And also knowing the exact difference, for example, the square root of n is actually growing quicker than log n. You could kind of figure that out just by doing some math in your head. Like I said, the log of 4 billion is going to be something like 32, whereas the square root of 4 billion is still going to be a very large number. But this is mainly to give you a high-level overview of how these time complexities relate to each other, because that's what's important. You need to be able to know how efficient your algorithm is. If you see your algorithm is factorial or exponential or even n cubed, you know it's not super efficient. You want your algorithms to be on the right side of this chart, though sometimes it's not possible. If you found this video helpful, please like and subscribe. It really supports the channel a lot. If you're preparing for coding interviews, check out neetcode.io. It has a ton of free resources. You can also get 10% off lifetime access using code NEET. Thanks for watching, and hopefully I'll see you pretty soon.